Hi there, this is Professor Shannon Gracey. Today we'll be going over section 5.6 from the calculus text by Larson and Edwards. This section covers inverse trig functions and focuses on differentiation. All right, so what I have found in my time as a teacher of calculus is that folks have not quite remembered their trig very well, especially not the inverse trig stuff. And it's important that you understand this. So what we're going to do is go ahead and draw these graphs by hand from negative pi to pi inclusive, and we will list the domain and range and all that good stuff. So go ahead, pause the movie, and warm it on up. Right? Okay, let's see how you did. So here we go. We've got our graph going from, this one's not that fabulous, going from negative pi, that would be negative pi over 2, and then pi over 2 and pi. All right, and then if we get, so here, remember that the range of the sine function goes from where to where? Good, it goes from -1 to 1 inclusive, okay? And here, so we'll have our 1, and we'll have our -1. So for our sine graph, if you recall, we're going to have an ordered pair at 0, 0, good. Pi over 2, 1. Pi 0. And then negative pi, -1. So this makes this an odd function, right? And then you've got your nice sine wave. I don't like that one. And you got something going on like that. Okay, so here we've got, this one is our f at x. Now, when I have restricted domain over here, what I'm after is, how could we make this guy 1 to 1? I mean, what domain values do we need to have as our inputs where we pass the horizontal line test? Because in order to have an inverse, you've got to have a 1 to 1 function. So if you think about it here, if you look at this portion of the graph, right, going from negative pi over 2 to pi over 2, do you see that we cover all possible range values, and this is 1 to 1. So what's going to happen is we're going to restrict our domain to that interval in red, okay? So our restricted domain is going to go from negative pi over 2 to pi over 2 inclusive. Okay, good so far? Sometimes the program gets a little grumpy. Okay, so we have an ordered pair at pi over 2, comma 1, and at 0, 0, negative pi over 2, -1, and negative pi 0. So notice that the input is the angle and the output is the function value. So here, if you just kind of look here, this ordered pair right here is going to be at pi over 4, and it's approximately 0.7, and that's actually negative pi over 4, negative 0.7, and then up here you'd have positive pi over 4, positive 0.7, right? And the reason I'm getting those additional order pairs is, as you can see, it's difficult to, we're basically going to just be working with that yellow portion of the graph, and we're going to flip the x and y values, or coordinates. All right, so coming back over here on our inverse graph, for the arc sine, you might, you can also write it like this. You'll see it both ways. We've got something like this going on, and so remember that your axes are going to change. They're going to flip. So the input is now going to be going from -1 to 1, because that was the range of the original function. And then we restricted the domain from -pi over 2 to pi over 2. And we'll put in a pi over 4 and a -pi over 4 here. So this will be x and this will be g at x. Okay. So our domain for this guy is going to be from -1 to 1 inclusive, and the range is going to go from -pi over 2 to pi over 2 inclusive. Okay, so far? Awesome. So now let's make our picture. What we're going to do is we're going to swap out these ordered pairs. So we had originally had a 0, 0, so we'll have a 0, 0 again. We had an input value at pi over 4 and then approximately 0.7. So at 0.7 we'll be at about pi over 4. And when we input 1, we'll be at pi over 2. When we input -1, we'll be at -pi over 2. And when we input -0.7, we'll be at -pi over 4. So here's what we got. Here we have -1, and that's -pi over 2. Okay, and making our picture, it's a real subtle curve, okay, and that's our inverse sine. So outputs are angles and inputs are the real numbers. All right, so for going from -pi over 2 to pi over 2 inclusive. All right. Know that the inputs are the real numbers and the outputs are angles. Okay, going from -pi over 2 to pi over 2. All right, so and there you go. You've got your arc sine at x graph. Okay, so now for cosecant at x, what happens is this. You might want to sort of dash in a little ghost graph of the sine function. So remember that was kind of like this. All right, and then from here we can get our vertical asymptotes. So our vertical asymptotes will be at wherever we cross the reciprocal function, which is the sine function, wherever that crosses the x-axis. All right, and then wherever we have a maximum, a relative maximum, you're going to have kind of a parabola looking thing opening upward, and where we have a minimum, you'll see it opening downward. Okay, so this guy is f at x. So where do you think we ought to restrict the domain on this one? So do you see that here, this here covers all of our negative output values, and over here this would take care of all of our positive output values. So if we restrict the domain from negative pi over 2, so this would end up being inclusive, right? But we have a vertical asymptote here. So we're going to have it look like something like this, right? Whereas, you know, the original one here, we could be inclusive, right, on our domain. Over here, we got to be, we have it to make sure we don't include the vertical asymptote. So our restricted domain will therefore be negative pi over 2, which is included, to 0, which is not included, union 0 to pi over 2, where we include pi over 2 and not 0. And the range is going to be, what output values did we have? We went from minus infinity to minus 1, the minus 1's included, union, positive 1 to infinity. Good so far? All right, so now with our arc cosecant graph, we'll have something along these lines. So we know that our domain, right, from the original is going to be the range of the inverse. So we'll have the vertical axis go from negative pi over 2 to pi over 2. Okay, and then the input values are going to be the range of the original. So let's look at what's happening here. Okay, what's happening with this graph is we have a vertical axis, right, at negative pi, or a vertical asymptote at negative pi, 0, and pi. So those become horizontal asymptotes. So our horizontal asymptotes will be here, here, and here. Okay? So we have ordered pairs at, on the original we had an ordered pair at negative pi over 2. Right? We had an ordered pair at negative pi over 2 and then negative 1. That had a negative in front of it. And then we had an ordered pair at positive pi over 2, positive 1, right? And our graph, if you look here, as you approach the vertical asymptote from the positive side of it, right, from the right side, you go up to positive infinity. As you approach the vertical asymptote from the left side, right, so from the negative side of it, you approach negative infinity. So translating that over to the inverse function, this is what will happen. So we'll have an ordered pair at 1 pi over 2 at -1 negative pi over 2, right? We're going to go to, as we approach from the positive side, we're going to go off to positive infinity, and as we approach from the bottom, the negative side, we're going to go to negative infinity. Okay? So our domain for this one is going to be what? Good. Minus infinity to -1 inclusive, union -1, or union 1 inclusive to positive infinity non-inclusive. And then the range will be from negative pi over 2 to 0, where we do not include the 0, union 0 to positive pi over 2. Okay? All right, moving right along. Now we have our cosine at x. So graphing, we will have, this will be our f at x. And the cosine function has an ordered pair at 0, 1, pi over 2, 0, pi -1, and then we have negative pi over 2, 0, and then negative pi is at -1. And again, at pi over 4, we'll be at about positive 0.7 at negative pi over 4, and then at pi over 4, we'll be back up there again. Let's get it better here. Okay. All right, so let's see what we've got. We've got a graph here. All right, and this guy here was pi over 4, 0.7, and then this guy was negative pi over 4, -0.7. Right? So where do you think we should restrict the domain this time? If we look here, do you see that from 0 to pi, we've got all of our possible range values? So if we restrict our domain, and this would be inclusive, so if we restrict our domain from 0 to pi, we'll be good to go. So that'll be 0 to pi inclusive, okay, and then our range is again from -1 to 1 inclusive. All right, so keeping that in mind, and for our inverse graph, we'll have our inputs will be from -1 to 1, and then we'll be going just from 0 to pi. So let's put in pi over 2 as well. And we can also do our pi over 4. And we're going to look at 3 pi over 4. Okay? So here, if you look over here on the original, as we're going, this is 3 pi over 4. So here, this would be 3 pi over 4, comma, -0.7. So it's a little different than our sine or arcsine graph. Okay, so let's check it out. So this is going to be our g of x, and so we had inputs at 0, 1 on the original, so we'll have 1, 0 on the inverse. And then we had an input of pi negative 1 on the original, so it'll be negative 1 pi on the inverse. And then we had at negative we had 3 pi over 4 and then negative 0.7. So on this guy it'll be negative 0.7, 3 pi over 4. And then we'll have an ordered pair here, and we'll have an ordered pair about here. So again, we've got a really subtle curve going. Okay, and that's our inverse graph. So the domain is going to be from negative 1 to 1 inclusive. The range goes from 0 to pi inclusive. Okay, so for our secant function, again, we're going to do a ghost graph, if you will. So 0, 1. So again, we've got graph looking something like this. Right. This should probably be a little more like this. Okay, so then our vertical asymptotes will be negative pi over 2, pi over 2. And so our graph will go up here. It's going to go down here and here. Okay, so far? All right. So this is our f at x. Okay. So where should we restrict the domain on this guy? What do you think? Where do we have all possible outputs? We'll go on the positive side here. Do you see all the possible range values are what I've highlighted in yellow? So if we restrict the domain from, this will be inclusive at 0. We'll go to pi over 2, which is a vertical asymptote. So we got to exclude that guy. And then we go on to pi. Cool so far? All right, so our restricted domain is what we have up here, which was from 0 to pi over 2 union pi over 2 to pi, where the pi over 2 is excluded and the 0 and pi are included. And then our range on this guy goes from minus infinity to minus 1, where we include the minus 1 union 1 to infinity. Okay, so making our inverse secant graph, we will have so this will be our x, this will be our g at x, and our it'll flip around, so we'll be going just pi over 2, 0, and then we'll have our input values. Will be like so. And here we go. So on our original graph, we had an ordered pair at 0, 1s. So what are we going to have over here? We'll be at 1, 0, right? Remember we had a vertical asymptote at x is pi over 2. Whoops, not there though. At x is pi over 2. And so what we'll have is, if you look here, if you come from the left side, if you come from the left side of pi over 2, right, you're going up to infinity. So as we come from the lower side of pi over 2, we're going to go right to positive infinity. Conversely, we had an ordered pair at negative, we had an ordered pair at pi, -1. So at -1 pi, we'll have an ordered pair, right? And so then we will go the other way. Okay? So now, check this out. Do you see that the slope of this graph is always going to be, the slope of this graph is always going to be negative, right? So G prime is always less than 0 on this guy. No. Do you see that the slope on this graph is always positive, right? Always positive. You'd always have a positive tangent line. So G prime at x is always greater than 0. Whereas over here, right, in the arc cosecant one, do you see that it's always going to be negative? This G prime at x is always less than 0. So keep that in mind for the later in the lecture. Okay. All right. So moving right along, the domain of our graph is going to be good, minus infinity to -1 inclusive, union 1 to infinity, and the range will be from 0 inclusive to pi over 2 non-inclusive, union pi over 2 non-inclusive to pi inclusive. All right, so next up we've got our tangent function. So the tangent function is going to have vertical asymptotes at negative pi over 2 and pi over 2. And we'll have a point at 0, 0, pi over 4, 1, and negative pi over 4, -1. So it looks kind of like that. So for this one, our restricted domain, you see, will just be from negative pi over 2 to pi over 2 inclusive. Or non-inclusive, sorry. Pi over 2. And then what about our range? Our range is from, perfect, minus infinity to infinity, non-inclusive. So when we make our inverse graph, what will happen is, this is our x and our g at x. So what will happen is at, remember at negative pi over 2 and pi over 2, we had vertical asymptotes. So we'll have negative pi over 2 on the range. Sorry about the dots. Rango, Rango. So these will be horizontal asymptotes. And then our graph will have an ordered pair at 0, 0, right? Our horizontal axis will be like this. Okay, and let's see, so we'll have ordered pairs at pi over 4, 1. Or sorry, in this graph it's 1 comma pi over 4. And then at negative 1, negative pi over 4. And our graph will look something like this. Okay? So the domain is going to be minus infinity to infinity, and our range will be from negative pi over 2 to pi over 2 non-inclusive. All right, last set. Here we go. So this graph will be, we'll have vertical asymptotes at x is 0 and at x is pi. So our graph will be at pi over 2 will be 0, and at pi over 4 it'll be positive 1, okay? And at 3 pi over 4 it'll be negative 1. So this guy is going to be decreasing, and it'll look something like this. And so the restricted domain, you can see, will be from 0 to pi non-inclusive. And the range will be minus infinity to infinity, non-inclusive. All right, so our arc cotangent graph will be x, g at x. So what we'll have is actually should be a little lower. Now we've got it all set up. We'll be going from, so we had vertical asymptotes at x is 0 and x is pi, so that'll make them horizontal asymptotes here. And we had an ordered pair at pi over 2, 0. So at 0, pi over 2, we'll have an ordered pair. At 1, pi over 4, we have an ordered pair. At negative 1, 3 pi over 4, we have an ordered pair. So it's going to go something along these lines. Okay? All right, so our domain is from minus infinity to infinity, and our range is from 0 to pi, non-inclusive. All right, so hopefully, you know, that was a good review for you. Here's some more stuff that's good to know. So arc cotangent at 1, if you evaluate the cotangent of both sides, well, we don't have both sides. So basically, we want to know at what angle input does the cotangent function have an output of 1. And you've got to also remember the restricted domains from the original. So the output of an inverse trig function is an angle, all right? Is an angle. So do you see that at cotangent at pi over 4 is 1. So our arc cotangent at 1 will be pi over 4. Now for part B, arc sine at negative root 2 over 2 we got to think of, when does the sine function have an output? At what angle does the sine function have an output at negative root 2 over 2? Well, 2 times on the unit circle, right? We have it at where and where? At 7 pi over 4 and at, good, 5 pi over 4. So 5 pi over 4 isn't in the range of our arc sine function, so we throw that out. 7 pi over 4 isn't either, but negative pi over 4 is coterminal with 7 pi over 4, so you do the negative angle. Okay. All right, so the arcsecant at 2 root 3 over 3, right, which is equivalent to 2 over root 3. So you're thinking of, at what angle does the secant function have an output of 2 over root 3? Good, pi over 6. Okay. And for D, arctangent at root 3 is going to be beautiful. It's going to be at pi over 3. Arc cosine at negative 1/2. Well, cosine at what angle gives you an output of negative 1/2? It's got to be in quadrant 2, right? So we're going to go to 2 pi over 3. And then our cosecant at negative root 2, we're going to have a negative angle. That'll be at negative pi over 4. Okay, so far? Awesome, awesome, awesome. All right, so now we'll learn how to solve the equation for x. So now we have an equation, so we can evaluate the tangent of both sides. And when we do so, we'll end up with 2x minus 5 is equal to tangent at negative 1. So 2x minus 5 will equal to negative tangent at 1. That's a negative angle identity. Isolating x, if we add 5 to both sides, we'll get 2x is 5 minus tangent at 1. And dividing by 2, we'll get x is 5 minus tangent at 1 all over 2. Good so far? And that's the exact answer. And it'll be good to, to check it using a calculator. Unfortunately, my graphing calculator is not cooperating with me. So I'll leave the checking to you guys. You always are great about telling me where there's an error. All right, so write the expression in algebraic form. So this is super important for not only for this class, but for calculus 2. So this is what you do. Here's the trick. You let theta, because the output of an inverse trig expression is an angle, right? So you let theta equal to arc tangent at 4x, right? Then you evaluate, good, tangent theta of both sides, or tangent of both sides. So on the left side, where we end up with tangent theta, and on the right side we end up with 4x. So tangent theta, if you write this as a fraction, is 4x over 1. So when you make your right triangle here, we have our angle theta, and the tangent in right triangle trig is the side, good, opposite the angle over the side adjacent. Good. And this will give us, using just the Pythagorean theorem, this will give us 16x squared plus 1 under a square root. So now we come over here and we say, okay, this is equal to secant at theta, right? Well, the secant function is the hypotenuse over the side adjacent. So we would get the square root of 16x squared plus 1 over 1, which is equal to root 16x squared plus 1. And you're all done. So when you learn a technique called trig substitution in Calc 2, that's what you'll be using, that technique for part of the problem. So here, what would we do? We would let theta equal to, beautiful, arc sine at x. Oops. Good. Sine of both sides. We'll have sine theta is equal to x, which is really sine theta is x over 1. So making our right triangle, we have the sine function is the side opposite over the hypotenuse. So using the Pythagorean theorem, we get the square root of 1 minus x squared. So coming back over here, we can say this is equal to cosine theta, which is equal to, so the cosine in right triangle trig is the side adjacent, right, over the hypotenuse. So this will just be root 1 minus x squared, and we're done. All right? Okay, so now we get into the calculus finally. So looking at this, you know, we do our same old, let's differentiate both sides with respect to x, right? And if we evaluate the sine function of both sides, we will get sine at y is equal to x over 1, right? And making our triangle, the angle this time is y, right? So before, I don't know if I wrote those in, this angle was theta, and I did it on the first one. Okay, good. So over here, we'll have the side opposite over the hypotenuse, and so this will give us root 1 minus x squared. So now, coming back over here, we would say, I'm just going to rewrite it here, y equal to arc, I can't spell today, arc sine at x. And so what we said is, hey, we could write this as sine at y equals x, because we know the derivative of the sine function and we know how to differentiate implicitly. So we'll have d dx of sine at y is perfect. It's going to be cosine of my something, which is y, right, times the derivative with respect to x of our something, y, and that's just going to equal to 1, because d dx of x is 1. So this will give us dy dx times cosine at y is 1. So isolating dy dx, we're going to get 1 over cosine at y. But that's the same as dy dx is secant at y. And then you look at your triangle. So the secant is the hypotenuse over the side adjacent, right? So at the end of the day, we'll get dy dx is equal to 1 over the square root of 1 minus x squared. And we're done. Now what you're going to want to do is just memorize that result, okay? But this is where it comes from. All right, so why don't you try arc cosine at x and see how you do. All right. So good, we'll be making our triangle. I'm sorry these got off track. So we'll have our y equals arc cosine at x So then, coming over here, evaluating the cosine of both sides, we will get cosine at y is equal to x over 1. And making our triangle, we will have our angle is y, and then we'll have side adjacent over hypotenuse, and this will end up being the square root of 1 minus x squared. So now we're going to consider cosine y equal to x. Differentiating both sides with respect to x, we will get, using implicit differentiation, I'm going to go a little faster now, we'll get dy dx times, good, negative sine at y is equal to 1. So dy dx will be equal to negative 1 over sine at y. But this is equivalent to dy dx equal to negative cosecant at y. Looking at our triangle over there, the cosecant is the hypotenuse over side opposite. So we'll get dy dx is equal to negative 1 over the square root of 1 minus x squared. Right? How'd you do? Awesome, awesome. Okay, so next up, what do we have going on? The arctangent. So we have y is arctangent at x. So over here, y equal to arctangent at x. What we'll do is evaluate the perfect tangent of both sides, and that will give us tangent at y is equal to x over 1 to make our triangle. So we will have the tangent is the side opposite over the side adjacent, and this will end up being 1 plus x squared under a radical. Okay, so now thinking of this as tangent y equal to x and evaluating the derivative with respect to x of both sides, we will have dy dx times secant squared at y is equal to 1. So dy dx is equal to 1 over secant squared at y, which gives us dy dx is equal to cosine squared at y. And so what is the cosine? It's going to be the side adjacent over the hypotenuse. So we'll have dy dx is equal to 1 over the square root of 1 plus x squared, all of this squared. So dy dx will be equal to 1 over 1 plus x squared. All right. So next up, what we'll have is the Arctangent function. Now remember what we had said. We had said that the derivative is always going to be negative for this one, right? So we're going to have to take that into account at the end. So we have y is equal to, leave some room here, arc cosecant at x, and then evaluating the cosecant at both sides, we will have cosecant at y is equal to x over 1, making our triangle. We'll have our angle is y, and then the cosecant function is the side, the hypotenuse over the side opposite, and so this will end up being the square root of x squared minus 1. All right, so over here, considering cosecant y equal to x, then differentiating both sides with respect to x, we have negative cosecant y cotangent y times dy dx is equal to 1. So dy dx will be equal to negative 1 over cosecant y cotangent y, which gives us dy dx is equal to negative 1. Nope, sorry, it won't be over. It'll be negative sine y times tangent y. And then looking at our triangle, to plug that in, we'll have dy dx is negative. So sine at y is going to be side opposite over the hypotenuse, right? So we'll have negative 1 over x, and then times tangent at y, which is side opposite over side adjacent. Now, this is where the trick comes in. We need to ensure that this is always negative. So to do that, what we're going to do is this. We're going to have negative 1 over absolute value of x times the square root of x squared minus 1. And that's going to ensure that it stays negative. Okay? All right. Here we go. Arcsecant at x. So, evaluating the secant of both sides, we will have secant at y is equal to x over 1, making our triangle. We have our angle of y. The secant function is the hypotenuse over the side adjacent. So that'll make this side here the square root of x squared minus 1. And then coming back, we will have secant at y is equal to x, differentiating both sides with respect to x. We will have, good, secant y times tangent y times dy dx, because it's implicit, and that's going to equal to 1. So isolating dy dx, we'll get 1 over secant at y times tangent at y. And this gives us, using our reciprocal functions, cosine at y times cotangent at y. And then plugging in the values from our triangle, we'll have dy dx is, so cosine at y will be, good, 1 over x, and then times cotangent at y will be 1 over the square root of x squared minus 1. Now we need to ensure that this one is positive, because remember this one always had a positive slope. So dy dx will be 1 over absolute value of x times the square root of x squared minus 1. And we're done. All right? Okay. So now we get to our cotangent at x. And we'll see what that one turns out to be. And then we'll work on some other problems. So y equals arc cotangent at x. And we will have to evaluate the cotangent of both sides. That will yield a result of cotangent at y is equal to x over 1. And then finding our triangle stuff, we'll have our angle of y, and then this will be side adjacent over side opposite, which is going to give us the square root of 1 plus x squared for the hypotenuse. All right, so now we'll have cotangent at y is equal to x, differentiating both sides with respect to x. We'll get, dun, 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 good, negative cosecant squared at y, and then times dy dx is equal to 1. Isolating dy dx, we'll get 1 over negative cosecant squared at y, which is negative sine squared at y, so I'll write it like this. And plugging in from our triangle, this gives us negative, so sine at y is going to be side opposite over hypotenuse. So 1 over the square root of 1 plus x squared, the quantity squared. So we'll have dy dx is equal to negative 1 over 1 plus x squared. And we're all done with that. How's it going so far? You can do it. Hang in there. Okay, so here we go. What have we found out? We found out that basically the pairs, right? There's 3 pairs of results that differ only by a negative sign. So here's the official derivatives of the inverse functions when we've got a potential function of x. All right. So here, do you see that our arc sine and our arc cosine derivatives just differ by a sign? So this is one pair, and then 3 and 4 are another pair, and then 5 and 6 are the third pair. Right? So these, you want to memorize this stuff and be able to use it. Right? So now we get into, being able to find the derivative of these functions. So we've got, these new formulas, and the new formulas are going to work in with all of our other rules. So we have arc sine at t cubed, right? So if you want to make a use of, I don't like showing it that way. I'll show you the way we've been doing it for derivatives. Okay, so we'd have d dt of both sides, right? So what we're going to do here is we'll have f prime at t is equal to, we're going to need to differentiate with respect to t the inside of the arcsine function, all right? And then divide that by what? So that arcsine would be the square root of 1 minus what's inside, which is t cubed, and that's got to be squared. So I'm just using the formula. So now our next step is going to be f prime at t is equal to, so we'll have a 3t squared in the numerator from that derivative over the square root of 1 minus t to the 6. So just rewriting it all in one color, we'll have our 3t squared all over the square root of 1 minus t to the 6. How's it going so far? Awesome. All right, so here we've got arc sine at x plus arc cosine at x. So differentiating both sides with respect to the independent variable x, we'll have g prime at x is equal to, so this derivative, remember, is going to be 1 over the square root of 1 minus x squared. So that's the derivative with respect to x of arc sine at x. And then the next one is negative 1 over the square root of 1 minus x squared. So at the end of the day, what do we get? We get g prime at x is 0. All right. Next up, we have a lot going on here. So there's going to be some simplification that's going to need to happen. So we'll have d dx of both sides. So this is going to give us y prime is equal to, so I'm going to write this out a little more. So we'll have d dx of this product, right? So this product x times arctangent at 2x, and then that's going to be minus 1/4, I'll bring that constant out, times d dx of 1 plus natural log at 1 plus 4x squared. So now this first product, just be careful. So y prime we'll have d dx of x times arctangent at 2x plus x times d dx of this arctangent at 2x. So that whole thing is going to relate to just the very first one, okay? That product. And then we still have this minus a quarter. Now, how do we do that derivative? Remember, we're going to do the derivative with respect to x of what's inside the log, which was 1 plus 4x squared over 1 plus 4x squared. That's the result for this one. So this whole derivative here is this so far. So now we'll have y prime is equal to the derivative with respect to x of x is 1 times arctangent at 2x plus x times. So this derivative here is going to be the derivative of what's inside. So d dx of 2x over, if you remember, that's going to be 1 plus what's inside squared. There's no square root on that one. Now, continuing with this guy, so that's working with that derivative. Continuing with this guy, we're going to have 1/4 times 8x over quantity 1 plus 4x squared. So moving along, this will be y prime is equal to arctangent at 2x plus x times 2 over 1 plus 4x squared. That's continuing work on this first one. And then do you see the 4 divides out some of the 8? So here what we'll get is minus 2x over 1 plus 4x squared. So now we'll get y prime equals arctangent at 2x plus 2x over 1 plus 4x squared minus 2x over 1 plus 4x squared. So do you see that these guys zero out? And at the end of the day, believe it or not, our result will be y prime is arctangent at 2x. Okay. So next up, I think that might be our last problem, is it? Nope, almost. So next up, we've got this guy. So again, differentiating both sides with respect to x, we will have dy dx equals. So this is going to be 25 times d dx of x over 5, right? And then in here we're going to have 1 minus x over 5, the quantity squared. then this other one is going to be a product. So the derivative with respect to x of x is 1, and we'll multiply to that root 25 minus x squared, okay? And then plus x times that derivative. So for that next derivative, remember, we're going to have 1/2 times our something to the negative 1/2, and then times d dx of our something. So, filling it all in, what was our something? Our something was 25 minus x squared. So, continuing, we will have dy dx equals 25 times 1/5 over the square root of 1 minus x squared over 25. Okay, so now we will have minus root 25 minus x squared plus x over 2 root 25 minus x squared which and then we'll have times the derivative, which would be negative 2x. All right, so now continuing dy dx, the 25 times the 1/5 is just going to be 5. Okay, and then we'll have 5 over, getting a common denominator, this is going to be 25 minus x squared all over 25. Then we'll have minus root 25 minus x squared, and then we'll have minus 2x squared over just x squared, because the 2's will divide out. So I'll have x squared over root 25 minus x squared. All right, so now, cleaning it up, we'll have dy dx equals 5 over root 25 minus x squared over 5 minus, do you see we're going to have a common denominator of 25 minus x squared, root 25 minus x squared, so if I get a common denominator here, this would end up being 25 minus x squared over root 25 minus x squared, and then we'll have minus x squared over root 25 minus x squared, which is going to give us, in turn, dy dx equals, we'll have a 25 from the first term, we'll have a minus 25 plus x squared for the second, minus an x squared. Oh, and I'm sorry. Here we go. I knew there was something hinky here. I needed to put grouping symbols around there. And so when I do that, I'll have the minus 25, the plus x squared, and this will end up being another plus. Okay, and that's all over the square root of 25 minus x squared. So dy dx is equal to 2x squared over the square root of 25 minus x squared. And we are done. Okay, so I think this is our last example. Yeah. So our last example is to find an equation of the tangent line to the graph of the function. So here, dy dx is equal to, good, we'll have negative 1/2 times 1 over the square root of 1 minus x squared. We're evaluating this at x equal to negative root 2 over 2. So with this will be, at that specific value, we'll have negative 1/2 times 1 over the square root of 1 minus negative root 2 over 2, the quantity squared. So cleaning it up, dy dx will be negative 1 over the square root of, that's 2 over 4, 2 over 4, so we would have 4 minus 2 all over 4. So dy dx is equal to negative 1 over root 2 over 2. So we'll get dy dx is equal to negative 2 over root 2, which actually is just negative root 2. Okay, so making the equation of our tangent line, the order pair negative root 2 over 2, comma 3 pi over 8. So our tangent line will be y minus 3 pi over 8 is equal to the slope, which was negative root 2, times negative root 2 over, x minus a minus is plus, and so we'll end up with this guy. Okay, and we're all done. So have a great day. Talk to you soon.